Okay, let's get started. So today we have a lot of stuff to cover. There will be a lot of math and new concepts that we will be introducing regarding reinforcement learning. We are certainly not going to finish today, and we'll probably take the entirety of next week to explore all of the common algorithms that people are using these days for RL, and also explaining why it's so important to learn. So this semester, unlike previous times I've taught this class, we will spend a lot more time on reinforcement learning. A large reason is because now we increasingly see developers of large language models spending more and more of their compute on RL as opposed to pre-training or instruction tuning. And there are a lot of cool capabilities that have emerged from this process. So we're, again, still going to be, in this class, focused on the basics, like reward models, basic algorithm to update our language model, and we'll get more and more complicated moving forward. Okay, just a point for logistics. So we did receive some API keys from Tinker, which is this service from Thinking Machines that lets you basically take your own data and use it to fine-tune or RL an existing open weight model. So I'm going to release a Google form either today or tomorrow for groups who are interested in using this service, because it's not relevant to some groups but very helpful to others. And please fill out this form if you want access to this platform for your project, and we will distribute the keys accordingly. I did ask them what if anything we should be considering in terms of usage and acceptable use policies, etc. They did not reply to that, so I assume you all will figure it out as you use the service. It does seem to be pretty useful for model training. You can, basically how it works is you use their API to kind of upload your training data set, and you can download the resulting model from their service to your local, your computer, or whatever you're using for inference. So it's convenient because you don't actually need any GPUs to start training these big models. Okay, so let us kind of resume where we left off. Oh, yes. Yeah. Yeah, so I just briefly looked into the documentation. They have one thing to mention about Tinker is everything that they support is powered by LoRa, so you're not going to be able to do any full SFT or anything like that. However, LoRa is still extremely powerful with, especially as the models get bigger and bigger. The question is, will you be able to change or try new training objectives? I suppose so, but I don't know how hard it is. I'll send a link to the documentation along with the form so you can check it out. Obviously, it would be a lot more useful if you could do that instead of using some pre-written functions. Yes?
So I looked at the website a while ago, and I looked at it again now, and it seems like they added more models. Is it a thing that's happening with them? Or?
Yeah, they're supporting a lot of the best open weight models. Yeah. They do also support a 230 billion parameter model that you can fine tune. It's one of the largest Quen checkpoints. Yeah. It's cool that you can do that, but practically speaking, you would still have to do inference with that model. Even downloading it and running it might be a challenge. So just keep all of that in mind. You still, even, you may want to use this service for more manageable, smaller models if it's relevant for your project. Okay, so let's just, okay. Where we left off last time was by talking about some of the limitations of instruction tuning, right? And we made a big list of all the things that are, issues potentially with doing SFT on these curated data sets. One important concept that we brought up towards the end was this idea of teacher forcing and exposure bias. And I just wanted to first go over this with an example so that we are all clear on why this might be a problem, and that will kind of serve as a jump-off point for reinforcement learning. So let's take a simple prompt, right? So here we're going to do instruction following, so our prompt will be an instruction like complete this Python function to return a list of even numbers up to n. So here we have a very simple instruction, and we might have some input context, like here is the function definition, and the model has to write the code for this. So in your ground truth, in your instruction tuning data set that you're doing SFT on, you will observe a correct program in response to this prompt, right? So your ground truth, what am I doing? Ground truth output. This is used in SFT, might look like this. You could have, some results list. You iterate over the numbers up to n. You add this number to the results list if it's even. And then you return the results. So again, very simple program. And your instruction tuning data set might consist of millions of these input instruction, input, output pairs. So one thing to emphasize while the model is trained to generate this ground truth output is that at each time step, model is fed the correct prefix, which is derived from this output. So when the model is predicting, let's say, this 0 over here, it receives the ground truth program to that point, right? Regardless of if, at this point, at this point, maybe range was not one of its most probable tokens, and if you sampled from the distribution at this point, the model might have produced some other function or variable. We always assume in SFT that the model's prefix is completely correct and comes from the ground truth. So now, the problem is really, let's say we want to use our model at test time, right? So we don't have access to any ground truth output. So if we're sampling from the model at test time with just this prompt, right? We don't assume access to the ground truth. The model can make severe errors during this sampling process, right? Like, let's say it makes an error in the very first line of this program that it creates a dictionary instead of a list. Now it could still do all of these things that are plausible, right? All of this code and logic could be completely correct. But here, like if it produces this append function, the program is just completely wrong, right? And you might not expect in your ground truth, you will never see errors like this, right? But here, this is a error made during decoding. It essentially changes all the subsequent tokens to be globally wrong, right? And this is just a simple example, but you can imagine more egregious cases where the model writes something that doesn't respect Python syntax, right? Or the model repeats itself over and over again, or other errors that you just don't observe when you have ground truth expert created outputs like you do in your instruction tuning data set. So the key thing is that the model never sees errors like these during SFT. And why would it, right? You don't want to train the model to produce errors, right? So why would you have add in errors in your expert curated outputs? You always are showing it the optimal, correct solution whenever that's possible. But during decoding, these errors can crop up and then they can propagate as you generate more and more tokens, right? And so how can the model make errors like these? Like why is it possible for the model to make errors? I mean, in this case, it seems quite obviously wrong, right? If we want to return a list, but how is this possible, these kinds of errors? Yes?
Because for a similar prompt, the correct answer may be to create a dictionary. And so since it's sampling, it sometimes samples from the dictionary.
Exactly. So remember, in all of these cases, we're sampling. Even if we're doing greedy decoding, the model could put more of the probability on a token that just doesn't make sense or violates the syntax or whatever, right? The model is not perfect, like we assume our expert labelers are, vast majority of their outputs are correct, right? But the model is not correct. We're teaching it to be more, behave more like those experts, but we can never guarantee, especially on a held out prompt, that the model will behave like a human expert would. And so it will always make errors. These are compounded by the sampling process that is non-deterministic. And so overall, this example and others like it demonstrate this kind of difference between the training time teacher forcing, which is we're always giving the model the correct previous tokens, so it never observes errors. But then at test time, we kind of take away these training wheels, and the model has to get every single token prediction correct in order to have a correct prediction. Okay, so does that make sense? The high-level intuition is during SFT, the model always gets the correct past tokens and is trained to predict the next word. At test time, the model has to predict the next word given its own past, not some expert labeled past. Okay, good. So now when we're talking about RL, we're really trying to get the model to kind of learn from its own generations as opposed to expert labeled demonstrations. Do you have a question?
Yeah, so when we're actually doing the SFT, and it's still doing just the next token prediction.
Yes.
Right? So at every point, suppose when I have the results are append, and it has to predict the append,
Mm-hmm.
Is the prefix at that point what the model has generated?
No. So when you're doing SFT training, the prefix is always the ground truth previous tokens from the data set, like the expert data set. The model's predictions are never used during SFT. That's what leads to this mismatch between training and test time. Yeah. Okay, so we probably want to improve the model's performance on its own generation so it can better handle and be aware of the kinds of errors that it makes, right? So a high-level motivation here is to improve our model without teacher forcing, which is what happens during SFT. Okay, so let's get to our reinforcement learning setup, which will enable us to do this. So let's say we have some prompt, and let's say we have done SFT, we have an instruction-tuned model. We'll call that our current model. So now I want to introduce some terminology. You will see in all the readings and the blog posts that people will use different terms to refer to the same thing within this like RL for LLM space. This model is basically the current model that we are in the process of updating to improve its capabilities. We will see it referred to as the policy model. Some common notations are P of theta, y given x. This means the probability of some output y given some prompt x under the current model, which is defined by theta, these parameters, right? And the thetas are getting updated. In some readings, you might also see this instead of P as pi sub theta. So you'll see things like this. We will stick with the former notation, but pi is more common in the reinforcement learning terminology to refer to policies. Regardless, all of these terms are referring to the current set of parameters that we have with our LLM that we're updating. Okay, so now let's say that instead of just generating one output from my model, I am going to sample several different outputs for this prompt. So let's say I sample an output y1, an output y2, and an output y3. All of these could be wildly different, right, because of the randomness in the sampling process. Also because some prompts are underspecified, like, write me a story about a cat. Others are much more constrained, right, like this Python programming example. So now, imagine a case where I have access to some human labelers, so a human rater. So this guy is going to read all of these 3 samples that are generated by my model, and he's also going to have access to the prompt. And the result of this process is our labeler is going to rank all of these yi's based on how good they are given the prompt x. So he might say that y2 is better than y3, which is better than y1. So let's say that we had access to some sort of human labeler who every time our model generated many samples, we could obtain reliable ratings on which samples were better than which other ones. Obviously, this is infeasible, right? There's no way we can have a human, like in real time, do this process. But if we were able to obtain kind of rankings of samples like this, then what we would really like, and this is the whole idea behind reinforcement learning, is we want to increase the probability of samples that are deemed to be winning, so samples that are ranked highly, right? We'll call these y sub w. Here, this means it's strongly preferred by our human raters. And we also would like to decrease how much probability the model places on losing samples, right? So this is strongly dispreferred. So maybe like Y1 in this case has a severe Python syntax error, and our human raters always rank it as the worst. Meanwhile, Y sub 2 here could be the correct program that if you run has no errors and gives you the list of even numbers. And so we want to increase the probability of predicting that correct sample and decrease the probability of producing some error-ridden sample. So note that here, unlike in SFT, we're directly dealing with the model's own generations. Y sub W and Y sub L are both sampled from the model directly, this P sub theta, our policy model. So we're not using expert demonstrations like we are in SFT. That's a clear difference. So these are all samples that the model can produce and it has produced during the sampling process, meaning they are somewhat probable. The model thinks they're likely, they're possible to produce. Yes?
What sort of algorithm is used to rank the YIs?
That's a great question. We will talk about that here. So let's just outline the limitation here. We obviously can't have human raters in the loop like this if we want to do training at scale, also with many diverse prompts, like where are you going to find experts who can reliably annotate all of these prompts, and so on. So the idea is maybe we can collect a huge data set of these human preferences offline. So collect a large data set of human preferences. So the idea is that given some prompt X, we want to know, and maybe like 2 samples, we want a human to tell us which of the 2 samples is better and which one is worse. And then we can set up this kind of pairwise preference data set. So let's say that we have sampled all of these things from our instruction-tuned model. All of the Ys come from instruction tuning. We send a bunch of samples to human raters and obtain their preferences. Ideally you would send each prompt and pair of samples to many different raters and have them, you might get a lot of disagreement, right? If I say write a story about a cat and I have 2 different stories the model generated, it can be quite subjective which one is a better story, right? Unless one of them has obvious grammar or style issues or is not about a cat, right? That would be kind of a disqualifying factor. But in most cases, with prompts like these, it's going to be really hard. On the other hand, as I mentioned, some prompts, it's very easy for anyone to distinguish which sample is better than the other. So let's say we have this data set, and there's many of these data sets that have been collected. The big labs spend a ton of money creating these kinds of preference data sets. The next step is, can we automatically model these human preferences so we don't have to have human raters in the loop? So basically, can we train a model that given X and 2 samples can predict which sample would be preferred by a human rater? That's the overall idea where we're going to. Do you have a question?
Yeah. So with the supervised fine training, one of the benefits, so the main issue I'm understanding is like, when you get out of distribution, you're completely cooked because you only train within like the correct distribution, right? But
yeah, and any of these errors are out of distribution, right? Because
and then you're completely lost.
Yeah.
But with this, what if like all 3 of your, if you're not training on like correct answers, maybe the pre-training is strong enough, but what if like all 3 of your answers are like one is less wrong than the others, but they're all wrong?
Yeah, that's a great point. So, maybe I have 3 really bad stories about cats, and we have some preference among them, but none of them is like an exemplary story, right? what happens. So we will see how the model that we're about to train can take that into account. So instead of having this setup where you're ranking different models, different samples, even though that's how it's trained, the idea is that for any single sample, you want a score associated with that sample. And that score is going to tell you how good or bad that sample is. So if you had 3 terrible stories about cats, ideally all of them would have a low score in this setup. And then you essentially want to train your model to maximize that score of any arbitrary sample. So that's where we're headed. Yeah, it's a good question. Other questions? All right, so the question now is, can we train a model to predict, I should say, on this data set to predict human preferences? Because if we have a model that does this, then we can now start scaling this up to a much larger collection of prompts and do a lot more updates. We don't have to pay a human every time we want something to be annotated. This model is called a reward model, and it is this topic is also subject to a ton of research nowadays. How do you train reward models that are not subject to what's called as reward hacking, where you might train your model on this data set and you think that your model is able to separate good and bad stories about cats, but really your model is just saying longer stories about cats are better than shorter stories, and it hasn't actually learned anything else. So there's lots of important issues associated with reward models that we'll get into. But let's just kind of formalize the inputs and outputs of a reward model. So we want our input to be a prompt X and an response that could be generated by the model, which we'll call YI. So this is just a model generation in response to that prompt. And our output is going to be a scalar score, just like a single number, 8.3 or something like that, which we will denote as this R of X and YI. So it's a function of the prompt and the model generation. All right, so now we can discuss how to actually train this model. So the ideal case is that this reward is high for good samples and low for bad samples. So how can we train this reward model given this preference data set that we have? Okay, so again, we're going to train on data set of human prefs, where we might have a prompt X, a preferred sample Y sub W, and a dispreferred sample Y sub L. The way we're going to model these preferences is using a well-known statistical model of preferences, which is called the Bradley-Terry pairwise preference model. And the use of this model for training language models specifically was first introduced by OpenAI in their Instruct GPT paper, which proposed the concept of RLHF, or reinforcement learning on human feedback. So they proposed this idea of first taking your pre-trained model, doing instruction tuning, sending a ton of samples to human raters from the instruction tuned model, training a reward model, and then using that to update your instruction tuned model. So there's a big pipeline here that was kind of pioneered by OpenAI and that is now used by almost every big lab. And we'll see some new developments to this pipeline later on in the semester. Okay, so in this preference model, what we really want is to measure the probability that one sample, which we'll call y sub w, is preferred over another sample, y sub l, given the same input prompt. So if we have this probability, we can actually use the human preferences we've collected to train a model that computes this probability. So the specific preference model that we're going to use looks like this. And again, this is very similar to some of the like softmax and things like that we've looked at in the past. So the idea is that if I want to compute this probability of like how likely is it that YW is preferred over YL given X, I'm going to compute this reward score for both Y sub W and Y sub L. And the likelihood that I prefer Y sub W is going to be the exponentiated reward X Y sub W over the normalized, basically the exponentiated y sub w plus the exponentiated reward of y sub l. So again, this looks very similar to what we've discussed for next word prediction with the softmax and so on, right? The only difference is instead of looking at the probabilities of a particular word, we are looking at the reward of an entire generation compared to the reward of another generation. But you can see that this forms a valid probability distribution, right? We're normalizing over the rewards of our two samples here, so we would get a probability of preferring y sub w and one of preferring y sub l. So if we're going to model this probability in this way, and we want to train a model to increase the likelihood of preferring the same sample that a human rater preferred in our data set, we need to turn this into a loss function, right, that we can minimize. And just like we did with next word prediction, we're just going to use the negative log likelihood of preferring the sample that the human preferred over the other sample. So our loss L is just the negative log likelihood of this thing in here. And you can do a bunch of math that we're not going to do, but is pretty straightforward, just a bunch of log math. So this simplifies down into this nice, clean formula, which is over here. So this function here is very similar to the softmax. It's the sigmoid function, which essentially the softmax function with two classes. And so let me write this here. Sigmoid x equals 1 over 1 plus e to the minus x. So if you look at this function, this is our loss function. You can see that in order to minimize your loss, you want to assign a high reward R to the winning sample in our data set. You want to assign a low reward to the losing sample in our data set. So intuitively, I can just write this out. Intuition to minimize loss, YW should get higher reward than YL. And so if you look at this, this loss here, you can see that if the reward assigned to both Y sub W and Y sub L is, the rewards are similar, the model is kind of unsure which one to prefer, right? So basically, as the difference between these two rewards increases, the model will become more and more confident that one of them is preferred over the other. So that's, again, the general intuition behind this. So we talk about the loss to train the reward model, essentially trying to make the reward of human preferred sample higher than the reward of dispreferred sample. But we haven't talked about the actual architecture of a reward model. Like, what does that network even look like? Luckily, we've already learned what it looks like, because it is just taking our instruction-tuned language model and fine-tuning it with a linear layer on top to get a single score out of this giant language model. So that probably sounds confusing. Let us maybe write it out more. We're going to put a scalar linear on top of the final layer last hidden state of our instruction-tuned model. So let me just draw out how this looks, and then we can discuss why we might want to do this over something that could be much simpler than doing this. So the idea is that, remember, our reward is a function of the prompt and a particular response. So let's say I have x and y sub w. This is my prompt and my sample. Actually, let me move this down here. Oops. Okay, so I'm going to put these into our favorite instruction-tuned language model that I've already created from doing pre-training and then doing fine-tuning over the expert data set that we've created. So at the end of the day, after going through all of the layers of this model, I get the final layer hidden states associated with this prompt and response, right? So what I'm going to do, if this is h sub n, the final layer last hidden state, I'm going to put this through a linear layer to get as output the reward, which is going to be a single score. So mathematically, this r of x, y, w is going to be my favorite linear layer equation, just a projection of the final hidden state at the final layer of this language model. Now, the reward is a single score. It's not a vector. And so this matrix here is going to have the dimensionality of 1 by the dimensionality of the hidden state, right? So when we do this matrix vector multiplication, we will receive a single number, which we're going to treat as our reward for this particular sample. And we are going to fine-tune the entire model using the Bradley-Terry loss that we just showed above to get our final reward model. Okay, so that's a lot of stuff. Let's kind of break down why are we using a language model as our reward model. So does anyone have any ideas why this might be a reasonable way to train a reward model, which again is giving you a score of how good a particular output is for a given prompt? Like, why do we need to use this instruction-tuned language model? Yeah.
Just like we need to both have the x and the y at the same time as a pair to feed into it. So that's why we still use. It's better to use this like instruction-tuned large library model than other.
Yeah. So essentially, if I want my model to give me a score of how good is this story about a cat, the model is going to have to understand the story. It's going to have to understand language. It's going to have to know if something is ungrammatical or irrelevant or incoherent. It's going to have all of these properties, right? And the one thing we know that to some extent has these properties is a pre-trained language model, right? And if we use an instruction-tuned language model, it additionally knows how to relate prompts to response, like instructions to responses, right? So this is kind of the best possible thing that we have at our disposal to use. However, instruction-tuned language model doesn't just give you a score out of the box, right? So that's why we're going to fine-tune it using this loss function. Does that make sense? So in practice, reward models are really big because they come from the base language models. There's actually a benchmark called Reward Bench that is just a ranking of different reward models. On that benchmark, you see models that have like 30 billion parameters or 70 billion parameters. They're huge, and their entire goal is just to give you this number of how good is a response. So through this, you can kind of understand the failure points of reward models, right? If the language model itself is incapable of judging the response to a particular task, right? Then the reward model score is not going to be trustworthy at all. So this happens in quite a few tasks, right? If you want your model to be able to perform some extremely complex task, your reward model might not be able to judge the quality of the response. And so you're not going to be able to use your reward model to improve the capability of the model on that task. So these are kind of limitations. Do you have a question?
Yes, so why are we only using the HN and not the previous hidden state?
Yeah, so this is just a design decision. You could, for example, average all of the final layer hidden states. You could put another transformer on top that just outputs a single score. There's many things you can do, but I think the intuition here is that your language model already has so many parameters that you don't need to add that many new ones in order to adapt it to this, this setting.
I see. So what would be like the final, these layers, like if it was just a transformer and we didn't want to like fine tune it or something, what would be the output of this?
What do you mean?
Like, I'm saying like previously, like when we had a transformer, when we gave it a prompt, it would give us an answer.
Yeah.
Now we're giving it a prompt and a
Response.
And
now we get a number.
We get a number.
Yeah, so this R here, let's just say, you know, as an example, this R could equal like 8.2. So we're not doing our softmax over all of the vocabulary anymore. We are simply just getting a number out of this. Another thing to highlight is I wrote fine-tune this model using the Bradley-Terry loss. If you look at this loss function up here, I actually need to compute two different rewards and subtract them, right? So what that means is in order to compute the loss, I need to do two forward passes through this reward model, one for YW and one for YL. And then I subtract the rewards and do the sigmoid, et cetera, before I do backprop. So actually doing this in PyTorch is really trivial. You just have one forward pass for your winning samples, one for your losing samples. In the batch, you subtract them and then call loss.backwards. So it's easy to do in code, but you can see that it's kind of computationally expensive, right? There's two forward passes if you're using a pairwise comparison. Yes?
The objective that we just saw,
Yeah.
that only to train the reward model?
Yes.
That to also train, like, the when we are doing the back propagation, we're doing it all the way through the LLM.
Yeah, so this loss here is just to train the reward model. But the reward model is defined as this entire LLM. So we're not only training this this W matrix here, which is our new parameter, but we're also updating all of the existing parameters in our LLM.
So it's the idea that doing this implicitly also makes the LLM
So the reward model that you're training here, right? This whole thing here turns into the reward model, right? It is no longer useful for generating words. Its parameters have all been specialized to the point where all it's good for is producing this scalar score where preferred examples get higher scores than others, right? There's no next word prediction loss or anything like that.
How do we use these results?
Yeah, so that's our next step is, let's say we have a powerful reward model that aligns well with the human preferences on some held out data set. How do we actually use the reward model to improve our current policy model that we are going to be updating? That's where we're getting next, but we need the reward model in order to do that. Other questions? Yes.
Just to clarify, R is based off the final instead of the final token.
Yes. All right, let me check on YouTube. Okay, a comment. We trained our parameters first using some training loss, and now we're updating them using a different loss. It feels to me as if we're taking an extra step. So you can think about it this way. If we were to train our reward model using a transformer initialized randomly, right, with no pre-training or instruction tuning or anything like that, we could still do this training, right? All has changed is the parameter initialization. However, the place you're starting from has no understanding of how language works. And if you think about the task that we're doing in reward modeling, it's very complicated. It requires the model to be able to judge the quality of a natural language response. So the only reason we're doing this is to kind of take the capabilities of language understanding that our model has learned and specialize them to this judgment task that we care about. So hopefully that explains. I do understand it sounds like we're doing a lot of extra work, but this extra work is really meaningful if we want a powerful reward model. Yeah.
Probably I have missed it. Like when they train this reward model, do they freeze the instruction?
No. So all of the parameters of the reward model are updated. You wanted to, so generally, like, you have a large collection of human preferences, and your goal is to as closely match this preference data set as possible with the training. So if you just train this final W here, this is not that many parameters, right? It's essentially a parameter vector. It's a 1 by D HID, so it might be like 1,000 dimensions. You really want more parameters in order to better model the human preference judgments. Good question. Okay, great. So let us move on then to the question that you asked: how do we actually use this reward model? And first, we will go over some kind of simple ways to use it to improve the output quality of a language model. And then we will start with our reinforcement learning setup after all of that. Okay, so just now let's outline the whole setup that we have, because now we have an instruction-tuned model, and we also have a reward model. The reward model originated from the instruction-tuned model, but now has a different set of parameters. So let's say I have a prompt X, and I'm going to pass this into my instruction-tuned model. And now I'm going to do some sampling. And let's say I get 2 samples from my model, Y1 and Y2. Now I can pass both of these samples into my newly created reward model. And the output of this reward model are 2 scores, right? So this might be like 8.2 and negative 5.3 or something like that. And note that the reward model also takes the prompt as input. So we have a setup that looks something like this, where we take our instruction tune model, we generate some responses, and we score them with our reward model. So how can we use this to get better outputs? The easiest thing that you could do is called best of n sampling. You might also see this called rejection sampling. So intuitively, this is very straightforward. We will generate I different samples given the prompt X, and then we will choose the prompt that has the max reward as scored by our reward model, right? So here, let's say I took my prompt X, fed it through my instruction tune language model, and sampled 64 different outputs. I can score each of those 64 outputs using my reward model and just decide to generate the one that has the highest reward, right? This approach requires no training. And so, it's preferable we don't have to do any sort of other modification to our model to use this strategy. But what are some limitations of doing this best of n sampling? Yeah. Yes. The main drawback is actually that this is extremely expensive. You have to, let's say, do n different decoding passes, generate n different responses in order to use this strategy. And remember, to generate even one response from your language model requires going token by token, doing the sampling strategy, building your KB cache, and so on. So this is a very expensive strategy. Nonetheless, it performs pretty well. So all of the more complicated things we'll cover later. In some cases, this best of n sampling can outperform those approaches. But that said, we really want to get an approach where if I just sampled one generation from my model, I would hope that it has a high reward. So we want to maybe modify our model to maximize the expected reward of any single sample. That would allow us to not have to generate like hundreds of different candidates and rank them with the reward model. Okay, so let's get to some training-oriented strategies. One thing that we could do if we had this kind of reward model and we were able to score different samples for the same prompt is that we could just run SFT on high reward samples. So perhaps if we did the kind of best of n strategy, right, and we found that one sample was much better than all of the other samples, we could just maximize the probability of that good sample given the prompt. This is actually a viable method. There's a technique called RAFT and many kinds of variants of this that will just do SFT on the high reward samples, and it shows pretty decent gains as well. So just as a question to make sure we're all on the same page, how does this SFT differ from what we're doing in instruction tuning, or what we've already done? Yeah.
In instruction tuning, the outputs are created by people, but here the outputs are those samples that are generated by the...
Exactly. So here, the outputs come from the model that we're actually training. And so we can just dynamically generate new outputs from the model. Like, let's say we call loss.backwards and optimizer.step, right? Now, from the new model that we have, we can sample new yi's and repeat this process with a huge data set of prompts. So we're always scoring things that are coming out of our current model. We're not restricted to the set of human-created demonstrations. Yes?
Then, like, if the model is also getting better now, shouldn't we also need to reward models?
Yes, this is a great point. So our model might be getting better and better and better, but its generations may also be changing, right? And so at some point, the distribution of the model generations will be very different from the instruction tune models generations, which is where the reward model was trained. So maybe now our reward model needs to be retrained or updated on the new generations from our model. This is a problem, again, with reward model training. I think general idea is that when you're updating your model with this reward model, it's likely not changing that much it's not deviating too much from the instruction tune model, so the scoring still remains similar. We will see though, like when we get more into reinforcement learning, how we can actually enforce the model to not deviate too much away from the instruction tune model so that we can maintain the reward model's ability to reliably score samples. But it's a good point, yeah. Ideally, we could retrain our reward model every time the policy model changes, but that's not what happens. Yeah, but it's expensive, right? And remember, like the way we've set it up, the reward model requires human labels in order to train. So, you know, it's complicated. Okay, other questions? Yes. What about what? Yes, you could do controlled decoding where you're trying to choose the highest reward next token instead of, you know, if you're able to decompose your reward model to score partial outputs, which you could do. This is something that people have tried too. I'm not going to discuss it in this class, but yeah, it's not as popular of a strategy as these things that I'm mentioning here. Yeah.
But here we wouldn't lower down the YL.
Exactly. So that is a drawback of this method, is that only the high reward example is getting. So basically, the result of this is that you're increasing the probability of the high reward examples, and kind of implicitly that would downweight all other samples. But in reality, you're not using any information from all of those samples that you've generated. So when we get to reinforcement learning, our goal is we take one sample from the model, we compute a reward, and we update the model to increase the probability of that sample if the reward is good. We update the model to decrease the probability of the sample if the reward is bad. So that way we use all samples, so we're sample efficient. We're not just generating a ton of samples and using just one of them. And we're also telling the model when it does something bad to not do that in the future, which method number 2 here does not actively do. Yes?
Can both of these still fall victim to the reward hacking that you brought up?
Yes, any of these strategies can fall victim to reward hacking, which again is when the reward model has kind of latched on to some quality of the output that doesn't actually match what a human would be considering when they're labeling their preference judgment. So length is the most common way that reward hacking can occur, because generally, if you have 2 responses to some prompt, a human is likely to prefer the longer output to the shorter one, just in isolation, because the longer output has, maybe it's more detailed or it has more information or whatever. However, if a reward model sees enough examples like this, it, regardless of the content of the longer output, can learn to prefer it. And so if you're doing best of n sampling, you might observe the highest reward sample being the longest. Similarly with this step 2, you might just be, and that's just one example. There's many ways that the model can do reward hacking, and it's really hard to figure out you know, what those are before you actually train your model using the reward. Okay. Oh, yes.
So here we're doing SFT on the reward model, not the instruction.
No. Sorry, I should mention this is on our policy model. Or the instruction tune model that we're, so this is, again, we are doing fine tuning over the model that's generating the response. You're using the reward model as a frozen thing where we're not updating it anymore. It's just giving us scores to tell us how to better update our model. Yes?
So, what does raft mean here again? Sorry.
I actually forget what raft means. It's some sort of reward augmented fine tuning or something like that. It's the paper that proposed this strategy. So I should say that. Yeah, I believe it's linked on the website, but it might not be. You can just Google Raft LLM fine tuning and find it. Okay, so our third strategy is going to be to use reinforcement learning to increase the probability of a good sample, meaning one that has a high reward, by a small amount. And also decrease the probability of a bad sample, low reward sample, with also a small amount. And here the amounts that we're updating the model to increase or decrease its probabilities are functions of the reward that our reward model computes. So if our reward model tells us that this particular sample is great, it has a high score, we want to increase the probability of the model producing this sample next time it sees the prompt. If it says that this output is really terrible, we want to decrease the probability. Okay, so one thing that at this point we should keep in mind is that this is a little bit different than SFT in this way that all of the responses, these Ys, are coming from the model's own distribution. So if the model, so let's say there's a very, very high reward output that the model just never produces, right? Then we will not be able to use reinforcement learning or any of these techniques, best of n sampling, to obtain that output, right? With SFT on expert demonstrations, expert outputs, we can actually change the behavior of the model to give high probability to things that it would never have produced otherwise, because we have our responses coming from a different distribution, this human distribution. But here, our responses are always coming from our model. So the model it has like 0 probability of generating the correct program, then none of these strategies is going to help it generate that program, because all of the samples that we take from the model are going to be wrong. So that is a limitation of this approach, and that's why SFT is generally used to inject like new model behaviors and do things like instruction tuning to get it to follow instructions better, whereas RL is used to kind of explore the space of generations that the model actually produces, and then kind of fine-tune it to prefer only good ones within that more constrained space. So hopefully that intuition makes some sense now. After we go over reinforcement learning more conceptually, then we'll return to this and hopefully it'll be more clear. Okay, so let's start in the next 5 minutes here to describe some of our high-level goals with reinforcement learning. So we have this reward function, right? And the idea here is that we want to maximize our expected reward of some sample y generated by our model given some prompt x. So across all possible prompts, if we take a sample from our current language model, we want the reward of that response to be high. That's our goal. So let's remember what an expectation is, just as some review. Intuitively, you can just view this as a probability weighted average of the rewards. So let's say we have prompt X. And then, so for this prompt, for all possible outputs Y, and there's infinitely many possible outputs, right, for a given prompt, right? The model can sample any word from the vocabulary. It can produce responses of any length. And so there's not a possible way to enumerate all possible responses Y. But let's say we were able to do so. This expected reward, which is using this E notation here, is just going to be the sum of the probability weighted reward. So if we have this P theta, which is giving us the probability of a particular response given this prompt, now we multiply the reward by that probability sum over all possible outputs Y, and we have our expected reward, right? And so what we really want is when we sample from the model, the reward should be as high as possible. That's our goal. So of course, it is impossible to enumerate all Y and compute this exact expectation. So what we're going to do is estimate this quantity using sampling. So we'll generally sample, use just one Y per prompt, or a small number of Ys. And the idea is that even if we just sample one Y for a given prompt, if we do this over a large enough collection of prompts, we will have kind of an unbiased estimate of the expected reward, the true expected reward. So in general, with RLHF, we will just be taking one sample per prompt and trying to maximize this score. Okay, so now that we've kind of defined what we want, let's just make this a little bit more formal. So the quantity that we want to maximize, we can call this J, which is our expected reward. And here we can just write this as, for a given prompt, we're going to draw some Ys from the distribution of our current model given that prompt X, right? So this, again, is our expected reward, and this reduces to this probability weighted average across, or rather sum across all of these samples that we've taken. So if we're going to maximize this quantity, so remember now this is different from what we were doing when we were training or fine-tuning a model where we were trying to minimize our loss. Here we're trying to maximize our expected reward. And so when we're going to adjust our model parameters, we're not going to subtract the gradient. We're going to add the gradient in order to maximize this J quantity. So in order to do so, we need to be able to compute this term dj d theta, right, which is going to be our gradient, the partial derivative of the loss with respect to all of the parameters in our current model. So if we write this out, if this is our j sub theta, now we're going to sum over all of the samples y, and we have our reward, and the theta actually only comes to play in this probability, right, of how probable is this sample given the prompt x. So that is py given x. So now, in the last couple of minutes here, we should note that it's actually tricky to compute this gradient because the process of forming y, the response, is non-differentiable, right? In order to generate a response, we make a series of hard decisions at each time step. So our model produces a distribution over the vocabulary. We make a single choice to pick like one of those words out of all of the V words, where we pick a word at the same probability that it is in the predicted distribution, right? But we're still making a single choice. Once we make that choice, we have no idea what the probabilities of all of the other words in the vocabulary are. And just like that, for every single word in our response, we make a hard decision. So there's no way that the gradient can flow through the sequence of decisions that I made. And so that's kind of the tricky part with reinforcement learning, is that you only observe this final response that's a product of all of these individual non-differentiable decisions. And so a lot of the kind of training algorithms that we'll talk about in the next class are basically tricks to kind of differentiate through the probability produced by the model of this sample rather than each of those individual decisions. So next time we'll start talking about an algorithm to compute this gradient and update our model called reinforce, and then we'll build towards more complex algorithms after that. So see you on Monday, and remember to fill out the Tinker form that I will send out if you want to use that platform.
The tinker you said is for fine tuning, right?
So